Alright, people, welcome back to the next lesson. And as I said in the last lesson, on the cantilevers, I think it was, that the next topic will be the theory of elastic bending, which is a brand new topic from Applied Mechanics. This is going to be brand new to you, but using concepts and terminology that we used before. It's not a massive section like the others, you'll be glad to know, but yeah, we need to do it. And as I said, it's the second last topic in theory of structures, and the last topic will be deflection, and then that will be the end of TOS, which is still a few weeks away. Okay, so people, I'm gonna flick back to a note that I have been put on Blackboard. If you go to the folder under Theory of Elastic Bending, there's a note there called Theory of Elastic Bending. Some notes, there's a note there. It's from a book, and that's chapter 6, Stresses in Beams, but we also call it Theory of Elastic Bending. Okay, so people, there I put in 2 or 3 pages there. I know I'm not gonna read all of it, I'm just gonna read some of it and point to a few things, and then we're gonna work through a few examples and see how this all works. Okay. Right, the theory of simple bending. I'll read through some bits and explain some bits as we go along. Let me just make this a bit bigger here. The theory of simple bending. An analysis will now be made of the distribution of stress and the various relationships that exist at a given section of a beam subject to pure bending. That's the next page. There we go. In order, now people, it's the theory of elastic bending. Now whenever people invent a theory, they like to apply it to some certain things, and with a few assumptions, hopefully the results will always be the same. Okay, and here are the assumptions. There's some sketches there, I'll talk about it as we go along. In order that correct mathematical methods may be employed, certain assumptions must be made as follows. Number 1, it says that the beam is in a state of pure bending. Now it's referring to this beam here. There's a beam, it's simply supported at its ends there, and it's got 2 loads of W kilonewtons, whatever it might be, at the ends there. And of course the dashed line there is how the beam will want to tend to bend over supports A and B. Okay, so along the top of the beam will be tension, along the bottom of fibers will be in compression. Okay, and if you went along and we put in some values, that will be the shear force diagram, and that will be the bending moment diagram, but just the bending moment diagram will actually be down there, across there, and up there. Why is that? Because in this country we draw the bending moment diagram on the tension side of the beam. Okay, sorry, I should say that, I should revise it. Okay, the tension side of the beam will be at the top, so this here will be the bending moment diagram for that over there. Okay, which is correct in our convention. Sorry, I made a mistake there. So there's the beam, and if it's supported like that, loaded like that, it's in a state of pure bending. That will be the shear force diagram if we throw it out, and that will be the bending moment diagram if we throw that all out there. Okay, number 2, the beam is of homogeneous material, okay, which is elastically isotropic, big words, and has the same value for Young's modulus in both tension and compression. Now briefly, what does it mean? When we make a beam, okay, when we pour a beam into its formwork there, it's made up of steel, and of course the concrete is made up of sand, stone, cement, and water. Okay, and of course if you just chucked it into a formwork, I'll draw a sketch quickly. If that's my form over there, like so, there's my form. And we just threw concrete in there, and we just dumped it in there, and we left it there to harden. Okay, and take the forms away. We'll have a rectangular concrete beam. Okay, but we just can't dump it in there. Okay, because we got steel bars in there. We need to vibrate it. Okay, why? So that the concrete can go down between the bars there, sit on the formwork there, so that the concrete can, so when formwork is taken away, the concrete is sitting as a rectangle and is all around the bars and sitting in the corners there. Okay, and of course if we take if that's my beam over there, like so, if that's my beam, let's say it's finished poured, and I take a cut through it like that, and I look at it like that over there, it'll be of a rectangular section with the bars there, okay, made up of sand, stone, and cement, and water which is not drying. Okay, now, and what it says here, number 2 there, the beam is of homogeneous material. Okay, what does homogeneous mean? It means that if we analyze the material, any bits inside there, okay, even though it's made up of different material like sand, stone, cement, that if we analyze its properties, it will be the same throughout the whole body of that beam. Is that possible? No, it's not exactly possible. Okay, because it is man-made. Okay, as the stone is blasted out of aquarium, and it's placed, it is vibrated, it is poked with the machine, and at the end of it all, the beam stands. Okay, so if we did an analysis on it, okay, the material isn't exactly homogeneous, but if it's correctly placed and vibrated, okay, as it's supposed to be, then we can safely assume that the material is of homogeneous material. That means if it's stressed out and analyzed, that means it will behave the same way throughout elastically. Okay, that means if we squeeze it or stretch it slightly, it will come, and if we don't over squeeze it or overstretch it and we release the forces on it, it will come back to its original shape. Okay, that means it will behave elastically. Remember the word Young's modulus of elasticity? We're talking about that property there. Okay, so but for us, we can assume that the material, whether it's steel or timber or concrete, is of homogeneous material. That means its properties throughout the body of the material is the same, and it behaves elastically. It behaves the same throughout the body of the material. Okay, there's Young's modulus. Number 3, the beam is initially straight, and all longitudinal fibers, the short word for that is long, bend in the form of circular arcs with a common center of curvature and a radius which is large compared with the dimensions of the cross section. Wow, that's a mouthful. Let's go over to the sketch on the page there. There's it over there. What it means is that there's your beam. Okay, the beam is placed in the form. The forms are supported. We have props under here. Props look like this. There's a prop there, sits under there like so, and we have a prop. Okay, so there's the ground. Okay, there's a prop there. It's jacked up. It's adjusted. So this prop and this bearer here, and that bearer there, okay, is holding up the formwork there, which is the molding. Concrete is poured in, and it's allowed to set and harden. And when it's all done, we take the props away, we take the formwork away. Maybe I should just name this here, formwork. Take the formwork away, and the beam stands. But before the props are removed and before the formwork is moved, the beam there is totally straight and horizontal. Okay, that's an end view. This is an end view, and this is an elevation on it. If we look on the end, that's what we'll see there, and that's what it says over here. It says there before the beam, before number 3 there, it says the beam is initially straight and all longitudinal fibers bend in the form of circular arcs. That means there's our forms are sitting over there, and before the forms are removed, the beams are completely horizontal. So that's the top of the beam, that's the bottom of the beam. If I go to my sketch, top of the beam, bottom of the beam, okay, and there's the steel running inside there, and there's a dashed line because we can't see it. Okay, so this here is a piece of the beam. Okay, if I take a piece like so, and the steel is running along a bottom there, and why is the steel at the bottom? Because if the beam is bending downwards, there's going to be tension in the bottommost fibers and compression in the topmost fibers, so therefore the steel is placed along the bottom. So there's my steel there, and this sketch here is just a piece of that beam, which is that over there. So there's the top of the beam, there's the bottom of the beam, and there's the steel running through the beam in dashed line. So why is it the dashed line? Because it's hidden detail. We can't see it. It's inside the concrete over there. Okay. So before the forms are removed, the beams are straight. And once the forms are removed, boom, there we go. The beam is bending. Okay. So it says beam initially straight with the forms in. Once the forms are removed, the beam is in bending. And of course, people, this here is an exaggeration. That means we've made it much bigger than what it actually is. The beam bends, but very slightly. Okay, and as I said in my sketch here, the beam bends downward, and because it bends downwards there's tension at the bottom, compression at the top. So we put tension at the bottom of the beam, and there's nothing at the top there. Okay, so there's the shaded area, there's the shaded area. Okay, so let me just go back to my note again. It says that the beam is initially straight and all longitudinal fibers, all the fibers running along the length there are what we call the longitudinal fibers. The fibers running along the length there. Okay. So so there's the topmost fibers, there's the bottommost fibers, there's the steel, and there's and because it bends, okay, it bends about point O, which is called the center of curvature, point O. And the distance from point O to there, from there all the way to there, is R, and that is called the radius of curvature, R. Okay. And of course, you can think for yourself there, that radius, because that curvature of bending there is so slight, that radius of curvature is massive compared to the dimensions of the beam. And when I say dimensions of the beam, I talk about BD, the dimensions there. Okay, so let me go back to my note there. It says the beam is initially straight and all long fibers bend in the form of circular arcs with a common center of curvature O and a radius which is large. Why is large? Because the bending is so slight you can hardly see it with your eye, compared with the dimensions of the cross section B and D. Okay, so that's what we're talking about there. And the neutral axis. Now, why is the neutral axis? If I take a cut along the beam there, my beam looks like this. The fibers at the top in compression, the fibers at the bottom is in tension there. If I take a slice at the top there, the fibers are in max compression. If I take a sliver of the fibers at the bottom there, they're in maximum tension. If I take a little cut of the fibers just a little bit below there, they're in compression but slightly less. And if I take another cut there along there, they're in compression but even more slightly less. If I take a cut along the bottom there, they are in tension but slightly less than at the bottom. If I take another cut over there, they are in tension but slightly less than over there. So what's going to happen? So the tension gets less. Compression gets less. And somewhere in the middle there, there's nothing happening. Okay? At that plane there, there's nothing happening there. Okay? So at that plane there, compression changes to tension. That is why we call that the neutral axis. Because if I could take that plane out and analyze it, it's undergoing no stress at all. That's why we call it the neutral axis. So if I go to my sketch there, it's called the neutral. Can you see that there? Okay. So somewhere in the middle. It's not in the middle. It's somewhere in the middle. Now, if I take a rectangular timber beam, there's B for breadth, D for depth, okay? And if I draw the x-axis, and I draw the y-axis like we know from section properties, okay? And where those two axes meet over there, that's the centroidal position of that there. And for the rectangular timber beam, if I draw a side view of that beam, like so, and I draw the x-axis running along there, we can't see it, it's an imaginary line, that there will be its neutral axis. For this rectangular beam, timber rectangular beam here, the neutral axis just happens to be on the XX axis. Ne? Just happens to be. But if we have a composite beam, meaning made up of steel and concrete, okay, with the steel running there, so somewhere in the middle, not exactly in the middle, but somewhere in the middle there, we're going to have the neutral axis of the beam over there. Okay, so that's a neutral axis over there. So there's a beam initially straight, there's a beam in bending. Okay, and there's the center of curvature, and there's just radius of curvature over there. Right, I'm reading the notes, I'm looking at my assumptions, and then number 4 there, it says there, the last assumption there, lateral cross sections remain plane and perpendicular to the neutral axis of the bending. What does it mean? It means that if I take a cut on my beam, say either there or there, I take a cut there, and I look at it edge on, like so, okay, it means that the beam remains like this. It says it remains in plane and doesn't deform. That means the beam will not do this. If I could deform it, okay, the beam remains square and rectangular. It doesn't deform in that way. Okay, that's what it says in the notes there. Lateral cross sections remain plane and perpendicular to the neutral axis of the bending. Okay, what it also means, if I take that plane there and I look at it edge on, that plane will look like a flat rectangle. It's not going to look like that. So that's what it means. We assume that it remains plane, it remains rectangular, it remains flat at the plane right angles to bending. That means there, if I take a cut along there, it will look something still rectangular like that, and not like that, and not like that. Okay, people, that's just that theory in a nutshell. And with all those assumptions taken into account, okay, I proceed down there, and of course the people that have gone before us, they do lots of mathematical calculations, which you will only get to be more familiar with. Once you get to the next level, you'll be glad to know. And once we do all the mathematics, and all the grinding, blah blah blah, we go through all the maths, and once we do all of that, and we get to that big formula over there, and that formula there, you can see, is the general expression for the theory of elastic bending. Okay, and I'm going to rewrite it and explain what they are and do some examples to see how we use them. Okay, right, let me just clean the board quickly here. Right, the board's clean, and I'm going to state the formula again. Okay, right, theory of elastic bending. Here I can make a nice straight line. Oh, that's nice. No, that was assisted. Let me take it off. There we go. Right, here's the formula. M over I is equal to F. This F is stress. Okay, you can either write it as F or stress. M over I is equal to that over Y is equal to E over R. Okay, maybe I'm going to make that a F. Okay, we can use the F rather. F and stress, the same thing. F sigma, same thing. Okay. People, in this section, that's the formula you need to remember. Okay, well, that R looks a bit like a thematic of Star Trek. Let me just fix it slightly. There we go. Okay, let me make it nicer. Oof. There we go. Right. But people, we normally use the formula. We normally use this formula with the splits only. Okay. With M over I equal to F over Y. Okay. We hardly ever use that over there. I'll explain what they are. Okay. Right. M there. M is the bending moment. Okay, in Newton meters or Newton millimeters or kilonewton meters, same thing. Okay, Okay, it's the moment as the beam bends and resists the load applied to it. That internal moment set up inside the beam, that bending moment set up inside there as a result of the load acting, that's M there. Okay, I, you'll be glad to know, is your second moment of area from the previous chapter. And what is it measured in? Yes, I'm sure you remember, millimeters to the fourth. There we go. Notice millimeters and meters, don't mix them up. Okay, so I is your IXX and your IYY. Same thing, nothing new. If it's your stress, I'll say stress in furthermost fibers, furthermost fibers in bending. In bending, when I say furthermost fibers, there's our beam. Okay, this is a rectangular beam. There's the YY axis, there's the XX axis. Sorry, Y, and that's cause its centroid position, which, as I said earlier, happens to be its neutral axis as well. Neutral axis, okay. It just happens to be because they coincident, okay. Fibers in bending, so F is a stress in furthermost fibers in bending, that is from there to the topmost fibers or the bottommost fibers. That's where we normally concerned with are. Okay, and what's the units for stress? What's the formula for stress? Stress is force over area, so to be newtons per millimeters squared from stress and strain. There we go. Okay, which is also the same units for Young's modulus of elasticity. Right, and what's Y? Y is the distance. Okay, Y is the distance from the centroid to the furthermost. I'm going to make this smaller. Let me just do the this is from the centroid to the furthermost fibers in bending. Okay, there we go. And it's a distance, so what is it? It can only be the famous millimeters. Okay, it's a distance. And what's Y? Y is, there we go, Y is when we did bar Y and bar X. Remember bar Y, bar X? Of course you do. Remember? Okay, that's Y top and that's Y bottom. Same thing. It's the same thing there. Okay, so that's IXX, IYY, that's stress or sigma, and that's Y top, Y bottom for what we got from section problem. It's the same thing. Okay, and E, I'm not gonna just make notes here. E is Young's modulus of elasticity. Young's modulus of elasticity, and it's measured in newtons per millimeter squared. There we go. Or it's in newtons per square meter. And R is, from the previous note I spoke, R is the radius of curvature. Or radius of curvature. And it's a distance, so it is in millimeters. There we go. Okay, so people, that's the full formula for the theory of elastic bending in symbol terms. That's moment of resistance, Newton millimeters or Newton meters or kilonewton meters. Okay, I is a second moment of area, millimeters to the fourth. F is a stress in the furthermost fibers in bending in newtons per millimeter squared, and Y is the distance from the centroid of the element to the furthermost fibers in bending, Y top, Y bottom, and it's a distance, millimeters. E is Young's modulus of elasticity in newtons per millimeter squared. We get it from the table. We normally know that because it's set by the manufacturer. And R is the radius of curvature in millimeters because it's the distance. But as I said there, when we use the formula, we mainly use it as M over I is equal to F over Y. We seldom use it for all of them like that over there. Okay, people, that's just a brief introduction to theory of elastic bending, and I will do a few examples to see how we use this in solving problems in theory of elastic bending. I shall see you in the next lesson.